Hello, welcome everyone, and welcome you all to the 10th class of this tutorial session of Thermodynamics course in NPTEL. I am Thananka Sutia, a PhD student at Center for Atmospheric and Oceanic Science in IISc Bangalore, and we'll wait for 1 or 2 minutes for everyone to join, and then probably we can start the class. Okay, hello everyone. Let me share my screen. Okay, fine. Okay, so today's class we will be doing sums related to psychrometry, that is basically the properties of the moist air. Earlier, all whatever air we have assumed it was a dry air, no amount of moisture was present, and we have not considered the properties of the moisture there. But in this session, we will be dealing sums related to the properties of the moisture. But before going to that, one question was left in the last class from the gases mixture, properties of the gases mixture, and from that I will do the sum first, and then I will go to the properties of moisture sum. Okay, so an ideal gas has the following volumetric analysis. Says that nitrogen has 60% by volume and carbon dioxide has 42% by volume. Now this percentage of the volume you have to convert it into mass percentage of each component. The second question is that what is the mass of 1 meter cube of this gas when pressure is 1.5 megapascal and temperature is 30 degrees Celsius. The third one is that if to find the specific heats of the mixture uh, at 300 Kelvin, if Cp of nitrogen and carbon dioxide are this one it is given, then if the gas is heated steadily through a steady flow process, then the temperature is increased by 120. You have to calculate the required heat transfer, and then the mixture undergoes an isentropic process from this. You have to find the final temperature. Okay, so let us begin. Now the first case, what is given to us, that each components, okay, and we are given the percentage by volume. Okay, so we are required to find out the percentage by mass of each of these two components, that is the nitrogen and carbon dioxide. Okay, so the percentage by volume is given to us. I will write this, and I may convert this into uh, just in a fraction of one. I can do that. Okay, now if you remember the earlier class, uh, PV equals to nRT. This is the ideal gas equation we can use because it is telling us that this is an ideal gas. Okay, so uh, we can write this as okay, and suppose there is any component A, so we can write this way. Now if we divide what what will we get basically? Na by nt. That means your volume fraction of any ith component is equals to the mole fraction of that ith component. Okay, fine. Therefore, x of n2 is nothing but volumetric fraction of n2. Okay, and the volumetric fraction of n2 is given to us as 0.6. Fine. Also, x of carbon dioxide is nothing but volumetric fraction of carbon dioxide, and that is nothing but 0.4. Fine. So I can increase one more column here, that the xi are also 0.6 and 0.4. Okay, now since we have to convert this into mass based analysis, so for that we will require the molecular mass of each of this component. Okay, so this molecular mass is in kg per kilomole, kg per kilomole. So molecular mass of nitrogen in kg per kilomole is what? We all know it is 28, and of carbon dioxide it is 44. Okay, so therefore the mass fraction okay, so therefore the mass fraction a mass of this contained in this one will be, I will write this one later on. Okay, so therefore xi times mi will be what? This would be nothing but 0.6 into 28. Okay, and this will be nothing but 0.4 into 44, and the units will be same, kg per kilo mole. Okay, so this will give you 16.8 this will give you, okay, so this, the total sum of this will be 34.4. Fine. So then we can calculate individual mass fractions. Okay, how will we calculate individual mass fraction? This is the individual mass. Okay, then this will be divided by total mass. Okay, this will be basically 16.8 divided by 34.4. Okay, so this is nothing but 0.488. Similarly, this will be nothing but 17.6 divided by 34.4. You can also do 1 minus this one, you will get the same answer. So that will be 0.512. Okay, so this finishes the first part. Now the next part is, what is the mass of 1 meter cube of this gas when P is equals to this one, and so that means now this mixture, you have to find the mass of the mixture. Okay, So the mixture is also an ideal gas. Okay, I'm using suffix m for the mixture. So for the ideal gas equation, Pm Vm is equals to mm Rm Tm. Okay, and the mixture, what are the things given? The pressure of the mixture is given to us as 1.5 megapascal. Okay, and volume of the mixture is given to us as 1 meter cube. Fine. Then the temperature of the mixture is given to us as 30 degrees Celsius. Which we can write as 303 Kelvin or 300 Kelvin if you want to write, doesn't matter. Okay, now we need to find mm, we need to know rm. Okay, so that means gas constant of the mixture. So we know this is nothing but universal gas constant, you can write this one as r star, okay, divided by molecular mass of the mixture. Okay, and what is the molecular mass of the mixture? We have already calculated this as 34.4. okay, and your universal gas constant was 8.314. okay, so this will be nothing but 8.314 divided by 34.4. okay, divided by 34.4. 0.2416 kilojoule per kg Kelvin. Okay, you have got rm. Now from this you can just calculate mm, that is mass of the mixture, that is nothing but pm vm divided by rm tm. okay, 1.5 into 10 to the power 3. Why it is 10 to the power 3? Because r is in kilojoule. okay, vm is meter cube 1, and 0.2416. temperature of the mixture is 303 Kelvin. okay. So you'll get this answer as 20.49 kg. okay, now find the specific heats of the mixture. okay, so specific heat of nitrogen and carbon dioxide are given, and then you have to find the specific heats of the mixture. okay, Cp of nitrogen, what it is given, 1.039 kilojoule per kg Kelvin. okay, 1.039 kilojoule per kg Kelvin. okay, and Cp of carbon dioxide is given to you as 0.846 kilojoule per kg Kelvin. 0.846 kilojoule per kg Kelvin. okay, so therefore Cp of the mixture will be we basically denote this one as what, suppose there are two compounds, then that will be C1 M1 plus C2 M2 divided by M1 plus M2. okay, now this one I can write this one as C1 M1 divided by M1 plus M2 plus C2 M2 divided by m1 plus m2. Okay, now these are nothing but mass fractions of these components. Okay, so that means Cp of the mixture is nothing but mf1 Cp1 plus mass fraction of the second component into Cp2. So that means if there are n number of components, then you have to just multiply the mass fraction of the individual components with this. Okay, so now this will be nothing but mass fraction of nitrogen times the Cp of nitrogen. What is the mass fraction of nitrogen? 0.488. Okay, 0.488. Okay, and what is the Cp of nitrogen? 1.039. 1.039. Okay, similarly this is 0.512 times 0.846. 0.846. Okay, unit will remain the same, kilojoule per kg Kelvin. Okay. This is 0.940 kilojoule per kg Kelvin. Okay, now since this is a mixture of ideal gas, so this will also be an ideal gas. So we know that for an ideal gas, Cp minus Cv is equals to R. This is only valid for ideal gas. Okay, so therefore Cv of the mixture is nothing but Cp of the mixture minus R of the mixture. Okay, we have already calculated the Cp of the mixture as 0.940, and also we know the R of the mixture as 0.2416. 0.2416 kilojoule per kg Kelvin. Okay. So this gives you 0.6984, 0.6984 kilojoule per kg Kelvin. Okay. Next question. Now this gas is heated in a steady flow process such that the temperature is increased by 120 degrees Celsius. Now you have to find the required heat transfer. Okay, that means the same mixture is now okay, now this same mixture, it is now heated. Okay, such that before heating the condition was 1, and after heating the condition becomes 2. Okay, so what we can write is from mass conservation, what we can write, dmCv by dt is equals to inflow mass rate minus outflow mass rate. Okay, where this is my control volume. Fine. Now since this is a steady flow process, so this will be equal to 0. So this will give you m1 dot will be equal to m2 dot. Okay, now from energy conservation, Okay, dECV by dt is equals to q dot minus w dot plus m1 dot h1 plus z1 plus v1 squared by 2 minus m2 dot h1 h2 plus z2 plus v2 squared by 2. Fine. Now again, since it is steady flow, this is gone. Okay, the work transfer anything is not given, this is gone. Okay, now m1 dot and m2 dot are the same. Okay, so from here we can write q dot is nothing but m dot times h2 minus h1 plus z of z2 minus z1 plus v2 squared minus v1 squared by 2. Now the change in kinetic and potential energy, they are not telling about anything, so this is also equal to 0. So finally you will get, okay, so we have assumed that this one is nothing but m dot. Okay, so from here you are left with q is equals to m dot times h2 minus h1. Okay, so that means if you want to get the energy heat input per unit mass, so that will be nothing but h2 minus h1. Now since this is an ideal gas, so this will be cp of T2 minus T1, but now this Cp will be nothing but Cp of the mixture, which we have already calculated. Okay, so the Cp of the mixture we have got at 0.940 0.940. Okay, and delta T T2 minus T1 is given to us as 120. Okay, 120, so that will be kilojoule per kg. Okay, hundred and 12.8 kilojoule per kg. Fine. Okay, now coming to the last question. This mixture undergoes an isentropic process from this one to this one, so you have to find the final temperature. Okay, so what it is given, P1 it's given as 0.1, 0.1 megapascal, and P2 is given as 0.2 megapascal, and T1 is given as 30 degrees Celsius, that is equals to 303 Kelvin. Okay, so now this is going an isentropic process. That means for reversible adiabatic process, what we can write, T2 by T1 is nothing but P2 by P1 to the power gamma minus 1 divided by gamma. But now this gamma will not be 1.4, this will be basically gamma is equals to gamma of the mixture, and gamma of the mixture is nothing but Cp of the mixture divided by Cv of the mixture. Okay, so we have already calculated the Cp and Cv of the mixtures. This is the Cp of the mixture and this is the Cv of the mixture. Okay, so the Cp is 0.940 and your Cv is 0.6984. Okay. 1.34. Okay, so this is your gamma. Now from here you can just calculate T2. T2 is nothing but T1, that is 303 times P2 0.2, P1 0.1, gamma minus 1 0.34 divided by gamma 1.34. Okay. So this will give you 361.26 Kelvin, and if you want to express this in degree Celsius, this will be nothing but 88.26 degree Celsius. Okay, so uh, this finishes your properties of gaseous mixture. So I will wait for 2 minutes or 1 minute for starting the next questions. Okay, any doubt you can ask me in between. Okay, so let us begin the questions from properties of the moisture. Okay, so the question is given is that moisture at 30 degrees Celsius and 1.01325 bar has a relative humidity of 80%. You have to determine the partial pressures of water vapor and air. Okay, then you have to determine the specific humidity, and then you have to determine the dew point temperature. Okay, so okay, so moisture properties, what it is given that so there will be some terms you need to know: dry bulb temperature. So this is nothing but the measured temperature measured temperature of moisture. That means whatever temperature it is measuring the thermometer, that is the dry bulb temperature. Okay, then you have to know what is dew point temperature. Okay, so if we cool moist air at constant pressure, comma, the temperature will decrease up to now. The temperature at which saturation happens, in other words dew is formed, okay, it is called dew point temperature of dead pressure. It is very important. Okay, so dew point process is nothing but a constant pressure process. So okay, you have to remember that here P is equals to C. Fine, then you have to remember another term, that is wet bulb temperature. Okay, wet bulb temperature, what we do here, we only decrease the temperature. We do not do anything with the quantity of water vapor. Okay, that means see, um, if there is a sample of moisture here, okay, and if you want to make it condensed, what you can do, you can start cooling at constant pressure. Okay, this is basically the dew point temperature. The another thing is that you start adding moisture to it. Okay, the moment you add moisture it will get evaporated, the moment you get moisture it will get evaporated, the moment you add moisture it will get evaporated. But at some time when the saturation will reach, no more moisture can get into this mixture. After that all the moisture will be remaining suspended in the air, isn't it? So in that case what we will get, a formation of we will get the droplets to be formed. That is the temperature that is basically called the wet bulb temperature. Okay, so in wet bulb temperature what we do, we add moisture. So automatically the pressure of, so this is basically PV equals to constant. Okay, that means the vapor pressure remains constant. Okay, so PV increases because you are constantly adding moisture. So if you add moisture, so by Dalton's law of partial pressure, so this partial pressure of water vapor exerted over the mixture will also increase. Okay, so these two things you have to remember. Okay, so now what it is given to us then in the question. Okay, so in the question it is telling us that a moisture at 30 degrees Celsius, so that means this is the measured temperature, that means this is the dry bulb temperature. Okay, so the dry bulb temperature TDB is given to us as 30 degrees Celsius. Okay, next a pressure is given. Now this is the pressure of the entire moisture, that means this is the total pressure of the moisture. Okay, so P total, this is basically P, I am denoting it as P. Okay, this is basically the total pressure of the moisture, which is nothing but 1.01325 bar, 1.01325 bar. Okay, so this is the total pressure. Next we are given the relative humidity. Okay, so relative humidity is given to us as 80%, that is 0.8. Now what is relative humidity? Relative humidity is mass of water vapor present divided by mass of water vapor that would have been present if it is saturated. That means in other case you can write this as mass of water vapor present divided by maximum mass of water vapor it can hold. Okay, so we denote this as mv for mass of water vapor present, and we denote this as mass of water vapor that would have been present if this is in saturated, as for the saturation. Okay, now suppose you want to okay, so let me write it in keep it this way. Okay, and its equation becomes in another form. For in order to do that, let me define two terms. Okay, so the first term I want to define is the mixing ratio. Okay, mixing ratio. Okay, this is nothing but mass of water vapor present per unit mass of dry air. Okay, so that means suppose this is the moisture, so it has got two parts, isn't it? That is water vapor and dry air. Okay, so we denote the mass of the moisture as m, we denote the mass of the water vapor as mv, and we denote the mass of dry air as ma. Okay, so this will be nothing but mv divided by ma. Now water vapor is an ideal gas, and dry air is an ideal gas. Okay, so from PV equals to MRT, what we can write, M as PV VV by RV TV is equals to PA VA RA TA. Now, this is nothing but the properties of gaseous mixture. Now, if there are two gases which are mixed thoroughly, then their volume will always be the same and their temperature will always be the same. Okay, so that means we can cancel out each other. So this will finally give you RA by RV into PV divided by PA. Okay, so now what is RA? This is the gas constant of the dry air, which we already know at 0.287 kilojoule per kg Kelvin. Okay, and this is the gas constant of the vapor, water vapor. Okay, and this is 0.461 kilojoule per kg Kelvin. So if you take this ratio, this will be nothing but 0.622 times PV divided by P minus PV, because pressure, this is it's pressure, the pressure of the moisture we assume as P, the pressure of the water vapor is PV, and the pressure of air is A. Okay, now this can be approximately written as 0.6222 times PV by P, because the PV is basically very small. Okay, so that means this can be approximately written as this one, but actual expression is this one. Okay, for the mixing ratio, and it is denoted by W. Okay, so this is the formula for mixing ratio. Okay, another one thing we need to notice, okay, so we are done with mixing ratio. Another thing is the specific humidity. And this is denoted as Q. So this is nothing but mass of water vapor divided by total mass of moist air. Okay, so whatever the mass of moist air is there, this total mass, that means the earlier was mv divided by ma, now this is mv divided by m. Okay, now again this is a mixture of your both what you call so this is the m is nothing but md plus mp, so this one I can write as p p v v v by r v t v. Okay, and this is nothing but p v by r t. Okay, now from this, once again, since this is a mixture, so mixture and the individual volume and temperature will be the same, so this will be again your r divided by rv into pv by p. Okay, now this r is approximately equals to rd. Okay, so that means this will also give you 0.622 times PV by P. What I mean to say is that we can use specific humidity and mixing ratio in exchange form. Okay, that means we can exchange them each other because there is not much difference between them. That is the main thing what I was trying to say. Now, what is relative humidity? Relative humidity is the mass of the water vapor that is present divided by the mass of the water vapor that would have been present in the saturation state. Okay, let me divide this by the total mass. So what will be this then? Q, and this will be nothing but QS, isn't it? Also this one I can write as W divided by WS. That means amount of water that vapor that is present divided by total amount of water vapor per unit dry air. Okay, this is the total. Now this I can express this one as 0.622 into PV by P divided by 0.622 into PV in the saturation state divided by P. Okay, so these two got cancelled, so this is finally PV by PVS. That means this is nothing but the ratio of the partial pressure of the water vapor divided by the saturation vapor pressure. Okay, so now let us come back to the question again. So T dry bulb temperature is given to us as 30 degrees Celsius. Okay, then P is given to us as 1.01325 bar, and relative humidity is given to us as 80%, that is 0.8. Okay, so now we have to first calculate partial pressure of water vapor and air. Okay, so partial pressure of water vapor first of all. So what is the partial pressure of water vapor denoted as PV? Okay, so this PV we need to calculate. How will we calculate? So we have already derived that RV is nothing but PV divided by PVS. Okay, so we know RH. If we know PVS, we can calculate PV. Now what is PVS? It is nothing but the saturation vapor pressure. Saturation vapor pressure at that temperature, at given dry bulb temperature. So we need to find out P saturation at our dry bulb temperature, that is 30 degree Celsius. Okay, so this will require steam table again. So you can find that this at 30 degrees Celsius, this is in megapascal. So for we just multiply by 10, so this will be 0.04247. Okay, so this is nothing but 0.04247 bar. Is it clear? So this is your PVS. Now from here, PV is nothing but RH into PVS. My RH is already given as 0.8, and I have already calculated that PVS as 0.04247 bar. Okay, point 0.4247 0.8. So this is your 0.0333976 bar. Okay, so this is the partial pressure of water vapor. Now partial pressure of of dry air. Okay, so that is nothing but PA. And so what will be PA? PA will be nothing but P minus PV. Okay, what is P? 1.01325 minus 0.033976 bar. Okay, 0.9793 bar. So I have told you already that this PA is not almost equals to P, that is 1. So this is also correct. We have got it. Okay. Next is calculate this specific humidity. Okay. So specific humidity, this is nothing but 0.622 into PV by P. Okay. Specific humidity that is Q is 0.622 into PV by P. Okay, so that is equals to 0.622 into 622 into PV is 0.03396 divided by 1.01325. Okay, so specific humidity is 0.02 kg per kg of moist air. Okay, so this is, you can also write this one as dry air because there will be not much different. Fine. Next is your dew point temperature. Okay, okay, so dew point temperature. Now in dew point temperature you keep PV constant and you continuously decrease the temperature. So this will be nothing but T dew point is nothing but T saturation at PV. Yes or no? Because suppose there is a constant pressure line, so you start cooling here and you will get the point at where this dew is formed. So this is basically the dew point temperature. Okay, so T saturation at PV. Now we already know the PV value, so that is T saturation at 0.0333976 bar. Okay, so we will go to the steam table and we'll look for the pressure tables. So this, remember, these are in megapascals, so we will add one more 0.003. So you can see here 0.0033976. So we can write this one as 0.00. Basically this is approximately equal to T saturation at 0.034. Okay, bar. So that means 0.0034 megapascal. Okay, so you can see here we do not have the values directly at 0.0034, so what we will do basically an interpolation between these two. Okay, so how will we do? By linear interpolation. So first let us write the values here. Okay, so T saturation at 0.036 bar is equals to 27.152 degrees Celsius, and T saturation at 0.032 bar is equal to 25.158 degrees Celsius. Okay, so using this data we will now do the linear interpolation, and from that we will get the answer. Okay, so now what we will do, we have to find out this one, so we'll do it by linear interpolation. By linear interpolation, what we will get, 0.036 minus 0.034 divided by 0.036 minus, we have to calculate at 0.034. okay, so this will be 27.152 minus 25.158, and this will be 27.152 minus T dp. Okay, so from here your T dp is simple, 27.152 minus, this will be cross multiplied and this will be subtracted. Okay, so 27.152 minus 25.158 times 0.036 minus 0.034 divided by 0.036 minus 0.032. okay, so this is your 26.155 degree Celsius. Fine. Okay, next question. Atmospheric air at this kilopascal has 30 degrees Celsius dry bulb temperature and 15 degrees Celsius dew point temperature. So now the dew point temperature is also given, the dry bulb temperature is also given, so you have to calculate the partial pressure of air and water vapor. Same, you have to calculate specific humidity, you have to calculate relative humidity, you have to calculate vapor density, and then you have to calculate the enthalpy of moisture. Okay, so what are the things given? So P is given as 101.325 kilopascal. Okay, then T dry bulb temperature is given to us as 30 degrees Celsius, and T dew point temperature is given to us as 15 degrees Celsius. Okay, So now you have to calculate the partial pressure of water vapor and partial pressure of dry air. Okay, so uh, suppose we reached the dew point. Okay, now if we further cool at constant pressure, it is already in the saturated state. So what I mean to say is that basically if we want to calculate PV, this is nothing but P saturation at dew point. Okay, so P saturation as dew point means P saturation at 15 degrees Celsius. Okay, and we also know that we want to calculate PVS, so that will be nothing but P saturation at T dry bulb, which we have done already in the previous thing. So that will be nothing but P saturation at 30 degrees Celsius. Okay, okay, so this is your 30 degrees Celsius, your this is 0.04247, 0.04247 bar. Okay, and at 15 degrees Celsius it is 0.017058 bar. Okay, so this is your partial pressure of water vapor. Okay, now that means the partial pressure of air PA is nothing but P minus PV. Okay, remember this is in kilopascal, so you have to express this in bar, so that will be nothing but 1.01325 bar minus 0.01758. Okay, 0.01758, 0.996192, 0.996192 bar. Okay, so this is now next is your specific humidity. Specific humidity, once again, it's nothing but Q is equals to 0.622 times PV by P. Okay, 0.622, what is PV? 0.017058. Okay, and your PV is P is 1.01325. Okay, zero point zero 1047 kg per kg of moisture. Okay, next your relative humidity, it is nothing but PV divided by PVS. Okay, we have already calculated both, so this will be 0.017058 by 0.04247. Okay, So it is equals to 40.16%. Okay. Now next is your vapor density. Vapor density. So that means rho v you need to calculate. Okay. So specific volume of dry air is what? VA is nothing but RA TA by PA. This is from the ideal gas equations. Okay, so RA, temperature of the dry air, is nothing but the dry bulb temperature, and the dry bulb temperature is given as 30 degrees Celsius. So this one I can write as 303 Kelvin. Okay, and the pressure is 1.013 into 101.325, this one kilopascal. So 101.325. So from here, specific volume of this one is 0. 0.858 meter cube per kg of dry air. Okay. Also, we can calculate the mixing ratio, that is 0.622 into PV by P minus PP. This will be mass of water vapor per kg of dry air, isn't it? So this will be 0.622. PV we have already calculated as 0.017058, 0.017058 divided by 1.01325 minus 0.017058. Okay. And 1.01325 minus 0.017058. So this will give you 0.0106 kg per kg of dry air. So you have volume per kg of dry air, you have mass per kg of dry air, water vapor. Okay, so therefore density of water vapor will be what? VA divided by, sorry, density na, so this will be W by VA. Okay, so what is W? 0.0106 okay, and this is your 0.858. you can see here, this is kg per kg of dry air, and this is meter cube per kg of dry air. So dry air got cancelled, so this one you'll get okay. So your answer is 0.012 meter cube per kg. Okay, so this is the density of water vapor. Okay, now next is calculate the enthalpy of the moisture. Enthalpy of moist air. Okay, so enthalpy of moist air, there is a formula. Okay, that is equals to 1.005 T dry bulb plus W times 2500 plus 1.88 T dry bulb, okay, where T dB is in degree Celsius, okay, and W is in kg per kg of dry air. Okay, this one you have to remember. Okay, so you just put it here, you just put it here, you'll get the answer. dB is 30, W is 0.0106, into TdB. So this will give you 57.25 kilojoule. Remember, this is also per kg of dry air. So in this chapter it is very important to mention the units also. Okay, so this is also basically per unit mass of dry air. Okay, fine. Okay, let us move to the next question. Air at 30 degrees Celsius dry bulb temperature and 25 degrees Celsius wet bulb temperature, it is heated to 40 degrees Celsius. Okay, then if the air is flowing at this much meter cube per second, so find the amount of heat that is added. Take the air pressure to be 1 bar. Okay, so T dB1 is given as 30 degrees Celsius and T wet bulb 1 it's given as 25 degrees Celsius. Okay, and T dB2 is given as 40 degrees Celsius, and volumetric flow rate of the air is given as 300 meter cubes per minute. Okay, and your P is given as 1 bar. Okay, so we have to calculate the enthalpy. Okay, and now this is heated from 30 degrees Celsius to 40 degrees Celsius, so this is a sensible heating is given to us. So enthalpy at the point 1, this will be nothing but 1.005 T dB 1 plus W1 times 2500 plus 1.88 T dB1. Okay, similarly H2 will be equal to 1.005 T dB2 plus W2 times 2500 plus 1.88 T dB2. Now whenever there is sensible heating, in sensible heating your PV and W remains same. Okay, so since this one remains the same, so heat Q is equals to H2 minus H1. Okay, so this will be basically 1.005 T of dB2 minus T of dB1 plus W into 1.88 into T of dB2 minus T of dB1, isn't it? Because this is your, these two terms will get cancel each other because these two are same on, and this W1 and W2 will be the same. Okay, and this entire thing will be, remember, this will be in kilojoule per kg of dry air. So we have to convert this into, okay, kilojoule per minute. Okay, so this is the entire task. So what are the things we know? The difference between these two, we have to calculate W, and then first our first motive will be to calculate W. Okay, and after that we have to convert this into kilojoule per minute. Fine. Okay, okay, so uh, then Carrier's equation will help us to solve this. Okay, in Carrier's equation what we can do, we can calculate the partial pressure of water vapor. Okay, provided you know the saturation vapor pressure that is corresponding to wet bulb temperature minus P total minus the same saturation vapor pressure corresponding to T wet bulb. Okay, my times T dry bulb minus T wet bulb divided by 1547 minus 1.44 T wet bulb. Okay, so this is an analytical equation. Okay, so now what we know the wet bulb temperature at 1. Okay, okay, so we know the wet bulb temperature at 1, so that means from here we can calculate your PV1. Okay, so PVS corresponding to wet bulb temperature 1 is what? So from steam table, PVS corresponding to the wet bulb temperature is your 0.031699 bar. Okay, now this is your 1 and this is again 0.031699. Okay, times 3 dry bulb. Okay, so 30 degrees Celsius and wet bulb is 25 degrees Celsius. Okay, so this is 30 and this is 25, and then this is 1547 minus 1.44 into 25. So from here you will get PV1, which is also equals to PV2. So 31699 minus 1 minus 0.031699 into 5 divided by 1547 minus 1.44 into 25. Okay, so here you will get this one is 0.0284 bar, and this is also my PV2. Okay, so from here I can calculate W1, which is also equals to W2, that is nothing but 0.622 times PV1 divided by P minus PV1. Okay, so that is your 0.018 kg per kg of dry air. Okay, so now we know everything. So from here I can calculate the heat in kilojoule per kg of dry air. Okay. Q is your 1.005 into this is 40 minus 30. Okay, then this will be W plus W is what, 0.018. Okay, then it is 1.88, and then it is 40 minus 30, and this will be your entirely in kilojoule per kg of dry air. Okay, 1.005 into 10 plus 0.018 into 1.88 into 10. Okay, so this will give your 10.3884 kilojoule per kg of dry air. Okay, so our next motive will be to convert this per kg of dry air to minute. Okay, now what we can do this, we can do this just by multiplying the mass flow rate of dry air. So our next motive will be to calculate the mass flow rate of dry air. Okay, so again from ideal gas equation, what we can write that mass flow rate of dry air is nothing but P of dry air volume flow rate of dry air divided by R of dry air into T of dry air. Okay, so mass flow rate of dry air, this is nothing but P minus PV times VA of dry air divided by RA into TA. Okay, so P minus PV is 1 minus 0.0284, and your volume flow rate is given as 300 meter cube per minute. So remember this is in bars, so you have to again multiply by 100 to express this in kilopascals, because this RA I will write in kilojoule 0.287, and this temperature is 30, so this will be 303. Okay, so this will be your 335.184 kg of dry air per minute. Okay, so this is the mass flow rate of the dry air. So therefore Q dot is nothing but m dot times your that Q, whatever you have got calculated. So that is basically MA dot. So MA dot is 335.184. Okay, and this one is your 10.3884, 10.3884. so this will be kilojoule per minute then. Okay, so now three four 81.93 kilojoule per minute. Okay, okay, next question. One stream of air at 5.5 meter cube per minute and 15 degrees Celsius 60% relative humidity flows into another stream of air at 35 meter cube per minute 25 degrees Celsius and 70% relative humidity. Calculate for the mixture assuming the total pressure is 1 bar, enthalpy, specific humidity and dry bulb temperature. So now two streams of air are getting mixed. Now you have to calculate for this mixture the enthalpy, the specific humidity of the mixture, okay, and the dry bulb temperature of the mixture. Okay, so let us write the given part. Okay, so volumetric flow rate of dry air for one part is given as 5.5 meter cube per minute. Okay, and temperature of dry bulb temperature of the first part is given as 15 degrees Celsius, and relative humidity is given as 60%. Okay, similarly it's given as okay, and it's given as okay, and relative humidity. Okay, so PVS at 1, that is nothing but P saturation at T dB1. Okay, and this one we got from steam table as 0.017058 bar. Okay, so therefore PV1 is nothing but PVS1 into RH1. Okay, so do you multiply with 0.6, you will get this one as 0.01023 bar. Okay, now again mass flow rate, we will get this one as P minus PV1 times V dot A1 divided by R of A TA1. Okay, put all these values, you will get this one as 6.586 kg of dry air per minute. Okay, fine. Also you will get W1 is equals to 0.622 into PV1 divided by P minus PV1. This will be 6.428 into 10 to the power minus 3 kg per kg of dry air, and also you'll get H1 is equals to 1.005 dB1 plus W1 times 2500 plus 1.88 T dB1. Okay, put all these values, you will get this one is 31.326 kilojoule per kg of dry air. Okay, similarly just altering the entire formulas, just putting here TdB1, TV1, what you will get basically as PVS2 from the steam table 0.031699 bar. Okay, then you will get PV2 as 0.022 bar. Then you will get m dot a2 as 40.015 kg per minute. Okay, and then you will get w2 as 0.014 kg per kg dryer, and also you will get h2 as 60.783 kilojoule per kg dryer. Okay, these are just the simple calculations which we have already done. These formulas are there, just replace 2 with 1. Okay, okay, so now the enthalpy of the mixture, that is nothing but m dot a1 h1 plus m dot a2 h2 divided by m dot a1 plus m dot a2. Okay, so m dot a1 6.586 into h1 is 31.326 plus 40.015 into 60.783 divided by 40.015 plus 6.586. So this is your 56.62 kilojoule per kg of dryer. Okay, this is the H of the mixture. Similarly, W of the mixture, which is almost equals to, we can, because we are required to calculate the specific humidity of the mixture basically, so that will be equal to m dot a1 w1 plus m dot a2 w2 divided by m dot a1 plus m dot a2. Okay, so w2 is 0.014. Okay, and w1 is 6.428 into 10 to the power minus 3. So this one is 0.0129 kg per kg of dryer. Okay, now you have to calculate this one are very easy. Now how will you calculate the dry bulb temperature of the mixture? Okay, so H of the mixture, we can also express this equation as 1.005 T dB of the mixture, isn't it, plus W of the mixture times 2500 plus 1.88 T dB of the mixture, isn't it? So from here we already know the H of the mixture is 56.62. Okay, we have to calculate these things. So what I will do is that TDB mixture I will take common. Okay, so from here it will come 1.005, and from here this will come W of the mixture into 1.88. Okay, that is 1.88 into W of the mixture is what, 0.0129. Okay, so this is this one, and plus W of the mixture is 0.0129 into 2500. Okay, so from here you will get TDB of the mixture is what, 56.62 minus 2500 into 0.0129 by 1.005 plus 1.88 into 0.0129. This is 23.67 degree Celsius. Okay, fine. Okay, so let us go to the next question. For a typical sample of ambient air, 35 degrees Celsius, 75% relative humidity, and standard atmospheric pressure, find the amount of moisture that is present in kg per kg of dry air. Okay, so you are given T dry bulb as 35 degrees Celsius, you are given relative humidity as 75%, and you are given pressure as 1 bar. Okay, this is the standard. So now you have to find the amount of moisture in kg per kg of dry air. That means you have to find basically W. Okay, and what is W? W is 0.622 into PV by P minus PV. Okay, so we know P. If we calculate PV, our this one is gone. Okay, so RH is nothing but PV by PVS. So now if we know the PVS, then we can calculate PV. So what is PVS? PVS is basically P saturation at T dB. Okay, so P saturation at 35 degrees Celsius. Okay, so now we go to the steam table. This one. Okay, so P saturation at 35 degrees Celsius is 0.05 bar. Zero point 0.05 bar. Okay, so from here PV is what, 0.75 into 0.05 bar. Okay, 0.0375. This is your PV. Okay, so now just put it here. W is equals to what, 0.622 into 0.0375 divided by 1 minus 0.0375. So this is your 0.024 kg per kg of dry air. Okay, fine. Now at 6 p.m. the air at a place is 25 degrees Celsius and 75% relative humidity, and the pressure is given as 1 bar. Now if the temperature of the place decreases linearly at the rate of 0.5 degrees Celsius per hour, at what time will the dew form? So what is the criteria that to formation of the dew, that this temperature should become the dew point temperature. Remember, this temperature 25 degrees Celsius is decreasing at the rate of 0.5 degrees Celsius per hour. Okay, now the starting time at when the temperature was this one as 6 p.m. So you have to find the time of the clock at which the dew will start to form. That means at which this temperature will become the dew point temperature. So our objective is to calculate the dew point temperature and the time required for the 25 degrees Celsius to become the dew point temperature. Okay, so at 6 p.m. Okay, so T dry bulb that is calculated from some thermometer is basically 25 degrees Celsius, and your relative humidity, it was 0.75. Okay, and the pressure is 1 bar. Okay, now from here how can you calculate the dew point? Okay, so dew point is what? T dew point is nothing but T saturation at PV. So that means the whole idea will be to calculate the PV. Okay, now how to calculate PV? We know RH is equals to PV by PVS. So if we know PVS, we can calculate PV. Now what is PVS? It is nothing but P saturation at your T driver. Okay, so that means P saturation at 25 degrees Celsius. So we will go to the steam table, and P saturation at 25 degrees Celsius is 0.031699. Okay, so this is basically 0. 0.03 bar, isn't it? So the P saturation at 25 degrees Celsius is basically 0.03 bar. Okay, so from here we can calculate PV is equals to 0.75 into 0.03 bar. Okay, so that is your 0.0225 bar. Okay, so the PV is your 0.0225 bar. Now then what will be my TDP? My TDP, that is my dew point temperature, is nothing but T saturation, that is corresponding to my PV. Okay, so now I'll go to the steam table and find out my where is my PV is there, and at that PV correspondingly the dew point temperature should be calculated. So I have to go to the pressure table, okay, and look for 0.002. Okay, yeah, so 0.0022. Okay, so we have at 0.0020 and 0.0024. Okay, so in between these two only we will be having the dew point temperature. Okay, so yes, fine. So from steam table, okay, so we record at 0.0022. So T saturation at 0.0020 is equal bar sorry sorry, T saturation at 0.020 bar is equals to 20 point, sorry, 17.495 degrees Celsius, and T saturation at 0.024 bar is 20.414 degrees Celsius. 20.414 degrees Celsius. So now what we will do, we will basically do a linear interpolation. Okay. Okay. So now by linear interpolation, okay, so what we want at 0.022. okay, so 0.024 minus 0.020 divided by 0.024 minus 0.022. okay, so this will be 20.414 minus 17.495 divided by 20.414 minus T of dew point. Okay, so from here my T dew point will be 18.95 degree Celsius. Okay, so that means this is my dew point. Now my 25 degrees Celsius should come down to 18.95 degrees Celsius, then only my dew will be formed. Okay, so therefore delta T required for dew formation is equals to what? 25 minus 18.95 degrees Celsius. Okay, so this is your 6.05 degree Celsius. Okay, so now then what is the time that will be required? Okay, so at every 1 hour 0.5 degrees Celsius rate it is decreasing. So the time, therefore time required to form dew is what? 6.05. this is the delta T that is required, and delta T per hour is 0.5 degrees Celsius per hour. Okay, so degree Celsius got cancelled, so that means this is the thing that is in hour. So the dew will be formed after 12.1 hours. So that means you can write this one as 0.1 into 60. That means 12 hours and 6 minutes. So it started at 6 p.m. okay, and after 12 hours and 6 minutes the dew point temperature is reached. Okay, so that means after 12 hours and 6 minutes, so the dew will be formed. Therefore required, okay, I have one more slide here. So required time of formation of dew is equal to 6 p.m. so it started at here plus your 12 hours plus 6 minutes. Okay, so that means this will be 6:06 a.m. So at this time of the morning, dew will be formed at that place. Okay, fine. Let us go to the next question. So air at atmospheric pressure and dry bulb temperature 40 degrees Celsius and wet bulb temperature of 20 degrees Celsius is humidified in an air washer operating with continuous water recirculation. The wet bulb depression at the exit is 25% of the depth of the inlet. So what is the dry bulb temperature at the exit? So basically this question is given to know what do you mean by wet bulb depression. Okay, so wet bulb depression is nothing. Wet bulb depression is equals to dry bulb temperature minus wet bulb temperature. Okay, so wet bulb depression at inlet is equals to dry bulb temperature at inlet minus wet bulb temperature at inlet. Similarly, wet bulb depression at exit is equals to dry bulb temperature at exit minus wet bulb temperature at exit. Okay, so what it is given that wet bulb depression at exit is equals to 0.25 times wet bulb depression at inlet. Okay, so from here we can easily calculate the dry bulb temperature at the exit. Dry bulb temperature at inlet minus wet bulb temperature at inlet. Okay, so dry bulb temperature at exit we need to calculate. So wet bulb temperature, this is the same water that is getting recirculated, so this wet bulb temperature will be remaining the same, and this will be 0.25 times 40 minus 20. Okay, so from here the dry bulb temperature at the exit is equals to 25 degrees Celsius. Okay, simple question. Next question. Air, a moist air sample has a dry bulb temperature of 30 degrees Celsius, specific humidity of 11.5 gram per kg of dry air, and molecular weight of air is given as 28.93 gram per mole, and if the saturation vapor pressure at 30 degrees Celsius is 4.24 and the total pressure is 90 kilopascal, then find the relative humidity. Okay, so we have to calculate relative humidity, and relative humidity is nothing but pressure, partial pressure of water vapor divided by saturated the partial pressure of water vapor if the water vapor would have been saturated. That means saturation vapor pressure. Okay, so the saturation vapor pressure at 30 degrees Celsius is given to us as 4.24. So our objective will be to calculate PV. If we know PV, then we can calculate the relative humidity. Fine. So what it is given to us? It is given to us the dry bulb temperature. Dry bulb temperature is given to us as 30 degrees Celsius, and then it is given to us the specific humidity. Okay, so W, that is given to us as 11.5. Actually specific humidity is not W, specific humidity is Q. Okay, that is 11.5 gram per kg of dry air. But as I have already told you that this Q and W, they are interchanged, so you have to just look at the units below. So since this is kg of dry air, so this is basically the W that is there giving to us. Okay, that means this is equals to your 0.622 P by PV by P minus PV is given to us. So if it would have been given the gram per kg of moist air, then this would have been PV by P. Okay, so that thing you have to be careful. Okay, so now so yeah, from here we can calculate this what you call PV. Okay, because we already know the P is given as 90 kilopascal. Okay, so now this is in gram per kg of dryer. We can convert this into kg per kg of dryer. So this will be 0.0115, that will be equal to 0.622. We have to calculate PV, we'll keep it as it is, and P total is given to us as 90, so that will be PV. Okay, 1.035 minus 0.0115 PV is equals to 0.622 PV. So from here PV is equal to 1.035 divided by 0.0115 plus 0.622, and this will be in kilopascal. Okay, so this gives PV as 1.6337 kilopascal. Okay, you know PV, you know PVS, so therefore your relative humidity is 1.6337 divided by 4.24. Okay, so that will be 38.5%. Okay, okay, so the next question: atmospheric air at 1.0132 bar has a dry bulb temperature of 30 degrees Celsius and a wet bulb temperature of 25 degrees Celsius. Okay, you have to compute the partial pressure of water vapor and the specific humidity, dew point temperature, relative humidity, degree of saturation, density of air in the mixer, density of vapor in the mixer, and the enthalpy of the mixture. Okay, so you are given P, that is 1.0132 bar. Okay, you are given T dB, that is 30 degrees Celsius. Okay, and you are given wet bulb, okay, that is 25 degrees Celsius. Okay, so now you have to calculate partial pressure of water vapor. So from Carrier's equation, which we have already came through, okay, if your wet bulb temperature is given and the dry bulb temperature is given, then Carrier's equation allows you to calculate the partial pressure of water vapor. So okay, so what is the Carrier's equation? PV is equals to PVS at TWB minus P minus PVS at TWB, okay, times TDB minus TWB divided by 1547 minus 1.44 TWB. Now what is PVS at TWB? So this is basically your saturation vapor pressure at wet bulb temperature. So what is the wet bulb temperature that is given to us? 25 degrees Celsius. So at 25 degrees Celsius, from the steam table you have to check the saturation vapor pressure. Okay, so this is the 25 degrees Celsius. So here the saturation vapor pressure is 0.031699 bar. Okay, so that is your 0.031699 0.03169 bar. Okay, so from here you just put it in this equation, Carrier's equation. So you will get PV as 0.03169 minus PV, this one. Yeah, so by calculation you will get this one as 0.02845 bar. Okay, because this rest all we know, this is in TDB is this one, TWB is in this one, and this TWB, this is 1547, this is P is this one, and this one is okay. So next question, you have to calculate the specific humidity. Okay, so we can calculate this one in kg per kg of dry air. So this will be 0.622 times PV divided by P minus PV. Okay, 0.2845 divided by 1.0132 minus 0.02845. So this is 0.0182 kg per kg of dry air. Okay, fine. Next is dew point temperature. Okay, so dew point temperature, so T dew point is nothing but T saturation corresponding to PV. Okay, you go to the steam table, see the saturation temperature corresponding to PV, you will get this one as 22.935 degree Celsius. Okay, next is calculate the relative humidity. This is nothing but PV by PVS. Okay, so put all the values, you will get this one as, so sorry, I have calculated the PVS, I have calculated the PVS at TWB. So PV is what we got as 0.02845, and if you look at the steam table PVS, you will get this one as 0.042470. okay, 66.98 degrees Celsius, that means almost equals to 67 degrees Celsius. Okay, next is your degree of saturation. Okay, so degree of saturation is mu. Okay, which is nothing but W divided by WS. So if you put here this one, so it will be 0.622 into PV by P minus PV, and 0.622 into PVS divided by P minus PVS. Okay, 0.622 will get cancelled out, so you'll get this one as PV by PVS times P minus PVS divided by P minus PV. Okay, so PV by PVS 0.02845 by 0.042470 times P is 1.0132 minus 0.042470 by 1.0132 minus 0.02845. Okay. Okay. So this will give you 66 percentage. Okay. Next is your density of air. So that means your rho A. Okay. So you have to calculate rho A. Now we know PA VA is equals to RA TA. So from here VA is equals to RA TA by PA is what? P minus PV. Okay. So this will be 0.287. Okay. And what is your TA? 30 degrees Celsius. So you can write this as Kelvin 303 and P minus PV. Okay. 1.0132 minus 0.02845. 0.02845. Okay, now this is in bar, you have to write it in kilopascal, so multiplied by 100. Okay, so 0.287 into 303 by 1.0132 minus 0.02845 into 100. So this is your 0.883 meter cube per kg. So this is the volume of dryer. So therefore density is what? 1 by VA. Okay, so it's 1.132 kg per meter cube. Okay, next is density of water vapor. Okay, so this we have already done. Rho V is nothing but W by VA. So what is your W? 0.0182 kg per kg of dryer. Okay, and this is your 0.883 meter cube per kg of dryer. Okay, so from here 0.0206 kg per meter cube. Okay, next is calculate the enthalpy. Okay, again enthalpy also we know the formula. H is equals to 1.005 TdB plus W times 2500 plus 1.88 TdB. Okay, put all these values. Okay, So you'll get this one as 76.67 kilojoule per kg of dry air. Okay, fine. Okay, so with this I conclude today's class. Thank you for listening.